The central limit theorem. Example 1. We have a population which is not normally distributed. That's what the ND stands for, normal distribution. Here's the mean and the variance for the population. We take a random sample of size 30. So the CLT can be used for two reasons. The primary reason is that the population distribution is unknown. It's not normally distributed. And the second reason is that we have a large random sample. So the distribution of the sample mean will be 4.5 for the mean here, and the variance will be sigma squared over n, so 2.25 divided by n, the sample size there. So now we have a normal distribution for the sample mean. And using this normal distribution, we can calculate probabilities. For example, this. What's the probability that the sample mean is greater than 5? So we just need to standardize the 5. There's the mean. There's the variance. So using the standardizing formula and the normal distribution, we can calculate this probability. So here's standardizing the 5. So subtracting the population mean from here. And you'll recall that in the standardizing formula, we divide by the standard deviation. This is a variance. So we need to square root the variance to get the standard deviation. And then we can use the normal tables to calculate the probability. Example 2. This time we start with the population, which follows a Poisson distribution. So the mean is 4.5, and we know the mean and the variance are the same for a Poisson distribution. Again, we take a large random sample. Sample size is 30. The CLT will state that the sample mean will be normally distributed. It will have a mean of 4.5, and the variance will be sigma squared over n. So there's the sigma squared value divided by n. Again, we can use this distribution for the sample mean to calculate probabilities. So we're standardizing 5. We're dividing by the standard deviation. So we're square rooting the variance here. So work out the z value, then use tables to calculate the probability. Example 3. This time we have some continuous random variable. So there's a population that's defined using this. So the first thing is to work out the mean and the variance for our continuous random variable here. And we can use some standard formulae from the OCR formula book. So page 7 in the formula book, we have a formula for the mean and a formula for the variance, this one here. So using these two, so work out the mean first, because we need the mean here to work out the variance. So the mean is 2/3. Doing some simple integration here and just following the formula from the formula book. We could do something similar with the variance, and the variance is 1/18. A random sample of 100 is taken from this population. So can we use the central limit theorem for the sample means? And the answer is yes, we can, because the underlying population distribution is unknown, it's not normal, and we're taking large random samples. So the sample mean will follow a normal distribution. The mean here is 2/3, and the variance will be sigma squared divided by n. So sigma squared, the variance of the underlying population, is 1 over 18. So we need to divide this by n. We need to divide this by 100 to get the following normal distribution. And then we can calculate some probability using the normal distribution for the sample mean. So standardizing gives us the following z value. And going to the probability tables, we have this answer. Example 4, this time we're starting off with a population which follows a binomial distribution. So the first condition of the CLT is met. The population is not normally distributed. We work out the mean and variance. We take a large random sample of size 70. The CLT states that the sample mean will have a normal distribution with a mean of 8 and a variance of sigma squared over n, so 4.8 over 70. Example 5, we're starting with a population which is normally distributed. So this condition that the population must not be normally distributed is no longer valid. So this time the central limit theorem cannot be applied. We take a random sample of size 5, so we cannot use the central limit theorem. However, if a population is normally distributed, there is no condition on the sample size. You can take a sample of any size, and the sample mean will be distributed with the same mean as the population distribution, and the variance will be sigma squared over n there. So remember, we're not using the CLT this time, because the underlying population is normally distributed. And there is no condition on the sample size if the underlying population is normally distributed. What's the difference in this example between calculating the probability that the sample mean is more than 5 and calculating the probability that x is more than 5? And you have to be careful here. When doing this calculation, you have to use this distribution. And when doing this calculation, x, you have to use the Poisson distribution. In example 3, we had a look at a continuous random variable, and we calculated this probability. So how would you calculate the probability that x is less than 0.68? Yeah, this one is specifically referring to the sample mean. So in its calculation, you have to use this normal distribution. Yeah, there's the sample mean. In the calculation of the probability that x is less than 0.68, we have to use our continuous random variable. So the probability that x is less than 0.68, using our continuous random variable, we're going to integrate from 0 to 0.68, like this, and that would give you the answer.